Hello everyone and welcome to another lecture. Today we will be taking a review on our knowledge of set theory. So what is a set? The first question to ask is what is a set? A straightforward answer would be that it's a collection of objects. Let's take a set A and let's say I have this set and I want to have cow, cat, dog, tiger. So these animals, they belong to some set. Alright. So the next thing we define is called element. What is an element? If your set has, let's say, prime as A1, A2, A3, each of these individual terms are called elements. Then, if we take a mathematical example, for example, we take the set of real numbers 1, 2, minus 1, minus 5, minus 0.15, etc. All of these are elements. And the next thing we want to see is something called a subset. So what is a subset? Let's say we have a set called S and we say that there is an element that is U that belongs to the set S, right? And if every element, that is let's take another set called S prime, and our previously we were talking about some set S, and we say that S prime and S are sets, and if every element of S prime is an element of S, then we say S prime is a subset of S. That is, let's say this has three elements, A1, A2, A3, something like this, and this has element of A1, A2, A3, S1, S2, sorry, small s, S3. So this S prime is denoted as a subset of S. And if S prime is a subset of S, but S prime is not equals to S, that is, this condition is satisfied but S prime and S, they are not equal, then we shall say that S prime is a proper subset of S. Now, after telling this, you can immediately conclude that S is also a subset of itself, but that is not a proper subset. Not a proper subset. But this S prime over here, it's a proper subset. And we can say that let's say we are taking the examples from our real and complex numbers. So let's say denote the set of real numbers as this bold R and the set of complex numbers like this. We can immediately conclude that this real number is a proper subset of the complex numbers, right? And we also say that this R is a proper subset of C, and we make an additional remark that R is contained in C. So, and the final thing to notice is just let's say you have a set 1 and you have a set 2, and the union is denoted with this. Diagrammatically it's the Venn diagram, that is, if it's S1, S2, this is the union, this whole thing, that is, let me choose another color, let's take a red color. So this whole thing is the union, and the intersection is given by, let's say, the blue color. So this is the intersection. So why are we talking about sets, right? Because the first thing we want to do today is that we want to define something called a field. So we want to define field. So we ask, what is a field? Note that this field will not be the same as you heard about in physics. Rather, we will try to take an abstract mathematical definition. So the way to define field is the following. So let me write as definition. And we write the definition as follows. Let K, that is let K, be a subset of complex numbers, that is C, this port C, and we shall say that K is a field. We shall say that K is a field if it satisfies some properties. So what are these properties? So the properties will be the following properties. The first property is that, let's say x belongs to K, y belongs to K, then x plus y and x times y belongs to K as well. This is the first property. These elements of the subset of the complex number will have to satisfy. That is, our x and y will have to satisfy. The second property will be that, let's take again x belongs to K, then minus of x also belongs to K. So this is another property. And if x is not equals to 0, x inverse 1 will exist and it will also belong to K. So this property tells us that if x belongs to K, then minus x also belongs to K. If these two things are true, and from the previous property, if x and y they belong to K, then xy will also belong to K and x times y will also belong to K. So using 1 into 2, we can say that, or we can conclude that x plus minus x, which is just 0, this also belongs to K, and x times x inverse, it's a multiplication, x times x inverse, that will be 1, will also belong to K. So this line is coming from using 1 and 2. Please keep this in mind. So as usual, you would see that there are three, if you open up any standard textbook on linear algebra, that you will find these three axioms or three properties that the elements of the subset will have to satisfy. But if you just take the two of them, that is the first one and the second one, this red box thing, this is the third, this will be emerging as the third one. So enough of our abstract definition. So let's write it down. No more abstract definition. more abstract definitions. We want to see some examples. So let's start. Let me choose the blue, it's a white color. So this will be the first example of a field. That is, first we want to prove that these real numbers, they form a field. So let's take any real number, that is x belongs to R and y belongs to R. So xy, if you add x and y, this is also a real number, so this one is trivially satisfied. If you multiply them, they belong to real number as well. For example, I could have taken x equals to 2, y equals to let's say 3. Then 2 plus 3 is just 5, which also belongs to the real number. And 2 times 3 is equals to 6, which also belongs to the real number. Now, what about the inverses, right? So, we have, let's say, x equals to 5. Let's say x equals to 5. So, minus x also belongs to real number, right? By our definitions. And we can see that minus 5 actually belongs to the real number. So, using this 2, we can write x plus minus x, that is just 5 plus minus 5 is 0. So 0 belongs to real number as well, right? And again, the inverse, that is x inverse, which should give rise to 1, that will also belong to the real number. And notice that we are taking x equals to 5, right? So let's say this 5 inverse 1 is just 1 by 5, right? And 5 belongs to real number, 1 by 5 belongs to real number, and this is giving us 1, which also belongs to real number. So we can see that the properties we required are satisfied, and we can say that this real number forms a field. Similarly, for rational numbers we can do it, but let's try to take another example, that is a counter example, that we want to see something that does not form a field. So let's take our example 2. And for this, we are going to consider the set of integers. That is, the problem statement is set of integers, that is z, denoted with this bold like z, does not form a field. So let's take an element. We are going to start with numerical values so that you guys understand better. So instead of xy, let's take x equals to 2. These are just positive integers, right? So not positive integers, sorry, just integers. So you can have positive and negative both, but they're just integers, no fractions are there. So let's take y equals to 3. You can see that x plus y is just 2 plus 3, which is just 5. It belongs to z, right? No problem there. X and y is just 6. That belongs to z as well. No problem there as well. And x plus minus x, that is 2 plus minus 2 is 0. Okay. Since we are not discarding 0, this also belongs to here. But the problem arises when you consider the multiplication. So this is where the problem arises. Let me emphasize this a bit. Problem arises when we look for the multiplicative inverse. The reason being, we are taking x equals to 5, right? And we want to find some x inverse 1 such that x inverse 1 is identity, that is 1. So the straightforward way to do it is just looking at this thing, right? Though this is not correct in a mathematician's point of view. First of all, the inverse should exist and you have to left multiply things and whatsoever, but let's just take it from a physicist point of view. So this x inverse 1 is 1 by 5, which does not belong to the integers. So this one counter example is enough to prove that z does not form a field. So we saw some brief definitions from our set theory, and we saw something called a field and the way to define it. The reason we are defining field because it is important for constructing a vector space. And another important remark is that the elements of the fields are numbers in general, and when there is no confusion we can call them numbers, but in general we will call them scalars. So I understand that this was a bit abstract, but these definitions will be important as we will advance further in this course. So I hope you enjoyed it, and I'll see you guys on the next lecture. Thank you.